Hey again, everybody. Here we are, Monday. Wanted to continue on and talk about our discussion of forces in 2D. We're going to continue on with the equilibrium idea. So just to review where we're going, or just to sort of preview where we're going today, here's December 17th on the calendar. First, wanted to review a problem that was very similar to the one that we did on Friday, or the ones that we did on Friday, dealing with equilibrium in 2 dimensions. Then we're going to continue on with that idea of equilibrium in 2 dimensions, but this time we're going to include gravity. So we'll see how that affects the problem, how it makes it a little different, but still the ideas are going to be exactly the same. So starting off today, we're going to do page 171, problem number 30. So I'm going to go here, and I'm going to grab problem number 30 down at the bottom of page 171. And it says, an object in equilibrium has 3 forces exerted on it. A 33 Newton force acts at 90 degrees from the x-axis, and a 44 Newton force acts at 60 degrees. What are the magnitude and direction of the third force? So, just to review our ideas from Friday, it says that we have an object in equilibrium, and we said that moving to 2 dimensions, that idea of equilibrium doesn't change, that the net force has to be equal to 0. But we did discuss that in moving to 2 dimensions, equilibrium now means that we have to have equilibrium on the x-axis, but also equilibrium on the y-axis. And that's what we're looking for in this, or that's how we're going to decide if this object is in equilibrium in 2 dimensions. So, it says, what are the magnitude and direction of the third force? We learned on Friday that that force that produces equilibrium we called the equilibrant. The force that produces equilibrium. So we are looking in this problem for F sub E. They gave us two other forces here, a 33 Newton force at 90 degrees, and then a 44 Newton force, a 44 Newton force at 60 degrees. So, starting off, first, we said the first thing we have to do is we have to set ourselves a frame of reference. And similar to what we did, or that's similar to what we did in the in 1 dimension, but now in 2 dimensions we have to account for 2 dimensions, right? So now our frame of reference is an xy coordinate plane. And on the x-axis we have a positive direction and a negative direction, and on the y-axis we have a positive direction and a negative direction. Remember, those 2 axes are, or those 2 dimensions are independent of one another. So we can do that. Alright, I'm going to take these 2, and hopefully this will work. Yeah, okay, good. We're going to group these 2 together, and then we are going to change that so that we are dotted, so we can tell the difference there. Make it a little smaller. Alright, and then we'll group all of these together, except I missed one. There we go. I'm missing this one on the bottom. Hold on. This is taking longer than I really wanted it to. There we go. Group. Okay, so now we have ourselves a coordinate system. So, we're going to put these forces on the coordinate system. First, 33 newtons at 90 degrees. Remember, we said the positive x-axis is generally 0. So we'll call this right here, that's our 33 Newton force at 90 degrees. Then we have a 44 Newton force at 60 degrees. That's going to look something like this. Longer than the red one because it's 44. Okay? So, we said the first thing we had to do was to split up our forces into components. If you look at F1 though, F1 is already on the y-axis. It doesn't have components. All of that force is on the y-axis, so we don't have to do anything with that force. But the blue one, right, the 44 Newton force, at that angle we said was a combination of this force this way and this force this way. So we know that This is 60 degrees because it told us that in the problem. And now we have our two components. So just to make it a little more clear, we'll take that out of here. We'll put this one here. We'll put this one here. This one I drew accidentally, so we'll get rid of that one. And we know that this angle is 60. This is 44. And so now we have enough information to find our two component vectors. I'm just going to do that real quick. Oop. So using our sine cosine identities, we get that this is 38.1, and then this is 22. Alright, so we said the next thing we did was we put all of these components together. So this one comes back here, and then this one, being on the y-axis, we can just lay that on top of the 33 Newton force that we know already. We've just figured out that oh goodness gracious, that this one was 38.1, and we established that this one was 22. We have to have equilibrium on both axes in order to have equilibrium in two dimensions. So the third force has to balance out all the other ones. On the x-axis, it's pretty easy. Looking now, all of our forces on the x and y-axis, there's only one component on the x-axis. So we need to have just one component on the x-axis going the other way, and that one has to be 22, because it has to balance out the other 22. Then on the y-axis, we have to balance out the combination of those two vectors, right? And this dotted green one has to be the sum of those two. So doing that in my head real quick, unless I'm mistaken, that would be 71.1. Alright, so we said that now those two green vectors become the components of the equilibrant force, the one that we need to produce equilibrium. This one being the resultant of those two vectors. We find the magnitude of the resultant using the Pythagorean theorem. So you plug that into your calculator. 22 squared plus 71.1 squared. Take the square root of those two, and you get 74.4. But we said that because it's a force, it's got to have magnitude and direction. So we need to find that angle theta to give us direction. We talked about on Friday that now we know all the sides of this triangle, but if we use the two sides that we figured out based on the components of the forces already given to us, using the tangent function, tangent is opposite over adjacent, so if we're trying to find theta, we'll pop in the opposite side, which you know is 71.1. The adjacent side relative to the angle that we know is 22. So we said we figure this out by taking the inverse tangent of both sides. And in doing that, we find out that theta is 72.8 degrees. But it's 72.8 degrees away from the negative x-axis. We said if we started at the positive y-axis, 90, 180, so we have to add 180 to this value that we calculated, and we end up with 252.8 degrees. So the equilibrant force in this problem is 74.4 newtons at 252.8 degrees, or if we go back up to the problem in sig digs, we would go 74 newtons at 250 degrees. Alright, so that was a review of something that we did on Friday. We are going to keep that theme of equilibrium, but now we're going to add in a force that we can't really get rid of, and that force is gravity. So, checking my agenda for today, chapter 7, page 171, number 34. So I'm going to go here, and I'm going to grab question number 34 that does have a picture that goes along with it. Yippee. Alright, so here's question number 34. It says, Joe wishes to hang a sign weighing 7.50 times 10 to the second newtons so that cable A attached to the store makes a 30-degree angle as shown in the figure below. Cable B is horizontal and attached to an adjoining building. What is the tension in cable B? Remember, tension is just a fancy name for another force. So this question is asking us, what is the force that cable B is going to have to supply to keep this thing from falling? There's a couple of things they gave us. First, they didn't give us force A, but they did tell us this angle right here. So we'll throw that angle in, and where it's 30 degrees from, we'll get into that in a second. But then the other thing that they gave us was that this sign weighed 750 newtons. We know what weight is. Weight is a fancy word for gravity, right? So we now know that the force of gravity acting on this object is 750 newtons. Remember, we don't have to do anything with that. We don't have to multiply that by 9.81. It's already done for us if they tell us that it weighs 750 newtons. So, with that in mind, I am going to go back to the previous problem, and I am going to grab our frame of reference. And then I am going to put it right over this picture, just like this, so that cable B runs right along the x-axis, cable A is in between the positive y-axis and the negative x-axis, and we go like that. Now, if we start putting forces on this object, okay, this object, because it is not falling, now this is sort of, an assumption you have to make, or sort of a jump that you have to make, but because of this object, if it's just sitting there, it has to be in equilibrium. And that means that the overall total of this object, total force, has to be equal to 0. Nothing changes from the previous problem. If we want equilibrium in 2 dimensions, we have to have equilibrium on both the x-axis and the y-axis. If we have that, we'll have total equilibrium. So we start putting some forces on this thing. Force B, we don't know what it is, but because it's a tension force, it pulls. And so it's got to be in this direction. That's an unknown. Force A, we don't know its value, but we do know that it acts right along this cable. That's what forces do. If it's a cable supplying a force, it's going to pull in that direction. The only force that we do know in this problem is actually the force of gravity. In all the other problems, we've just neglected that. We've been looking at it like from the top. But here, because we're looking at it from the side, gravity plays an important role in this problem. And it told us that gravity is 750 newtons. Okay. Here's where we take advantage of our definition of equilibrium in 2 dimensions in order to solve some things about this problem. This force A, the red one, it is not on the x-axis or the y-axis of the problem that we have, or the coordinate system that we have chosen. And that means it has components. It has a component that goes like this along the negative x-axis, and it has a component that goes like this along the positive y-axis. In essence, what we've done is we've taken out this force, force A, and replaced it with these two dotted reds. we said that the component vectors of a force are the simultaneous forces x and y, or horizontal and vertical, the end result of which is this diagonal force, right? These two forces, the two components, are acting simultaneously to produce this force. So, we'll just remove that for now. We actually know one of those component vectors, even though we have no idea what this force is. Because we have to have equilibrium on the y-axis, if we look at the y-axis in our problem, there are two forces. There's the gravitational force pulling down on this object, its weight, and then there is the y component, or the vertical component, of force A. Those are the only two forces on the y-axis of this drawing. Because equilibrium says that we have to have zero net force on the y-axis, that means that this upwards component has to be 750 newtons in order to balance out the gravitational force. That doesn't get us what we want to know, but hopefully you can make the jump. If we then look at the x-axis, there's only two forces on the x-axis. There's cable B, which is what we're looking for, and the horizontal component of cable A. If those are the only two forces, and as we see in the drawing, they point in opposite directions, they have to be equal to one another. That's what equilibrium on the x-axis means, which is one of the conditions to have equilibrium total. Now, we don't know what this x component is yet, but we can start making ourselves a triangle that looks something like this. We know that that component is 750. We don't know what this component is, but we do know that this is 30 degrees. Now we've got a side and we've got an angle, so we can figure out what the other side is. Technically, we could figure out what the tension in cable A is if we really wanted to. We could figure out what the hypotenuse of this triangle is, but that's not what the question asked us for. We've just established that this horizontal component is the one that's equal to the tension in cable B. So we can just find this horizontal component and we'll be good to solve our problem. I'm going to call this F of A along the x-axis because it's the x component of that force. This is force A. We don't know what it is, but we know this is the x component of A. So, based on the angle that we have, 30 degrees, we are looking for the opposite side of the triangle from the angle that we know. We know the adjacent side of that triangle. The relationship between opposite and adjacent is given to us by tangent. Now, we've used tangent before the last couple of problems. We're not going to use it in the same way in this problem because we know different things. First of all, we know the angle. It's 30 degrees. So we plug in 30 degrees for theta. We don't know the opposite side, but remember I called it the x component of force A, or the horizontal component of force A. We do know the adjacent side. It's 750 newtons. Now we can do a little math and find out what the x component of force A is. So I find out what tangent of 30 is, right? And then I can multiply that by 750, and I find out that the x component of force A is 433 newtons. And that means, because of the fact that we have equilibrium on the x-axis, this is on the x-axis, but this is on the x-axis as well. So if I know what this number is, that means I know what this one is. So F of B, the tension in cable B, has to be equal to 433 newtons. No need for direction here. because it's in the problem, but we could say, if we really wanted to be technical about it, at 0 degrees because it's right along the positive x-axis. Yeah. Good there? Hopefully, because you can't really ask questions, now can you? So, one more problem just to sort of sum up this. Going back to my agenda for today. On page 151, there is an example problem, and that example problem is called creating equilibrium. So I'm going to wait for my computer here, and I'm going to grab this problem. So this problem says a 168 Newton sine is supported in a motionless position by 2 ropes that each make 22.5 degree angles with the horizontal. What is the tension in the ropes? So before we go ahead and set up our unknowns, let's make sure we have a little picture of what's going on. First, there's a sine. What kind of sine? I don't know. I'm going to make mine just a square because it's boring. Then I'm going to get myself my frame of reference that I've been using, because in 2 dimensions, right, that's our frame of reference. So I'm going to paste it right here. And to make my life a little bit easier, I'm going to place the x-axis right on the top of my sine. It says that there are 2 ropes that each make a 22.5 degree angle with the horizontal. So that means there's a rope here, and that this angle is 22.5, and then there is a rope here, and this angle is 22.5. So we got those 2. There's also a third force. It says a 168 Newton sine. If it's giving us a value for the sine in newtons, that means it's giving us F of g. That's the weight. So the weight of this object is 168 newtons. If we put that on our drawing, weight, gravity, always acts straight down. So we have a third force that is acting on this sine. Generally, we draw our forces starting from the beginning of the object, but because of the way that they gave us the angles in this problem and what our frame of reference looks like, I decided to start it up at the top. Okay, getting back to the problem at hand. It says, what is the tension in these ropes? So, we have a red rope, and we also have a blue rope, right? So I'm going to call force red rope, that's one of our unknowns, and then force blue rope, that's our other unknown, right? We don't know the values of those, but we do know that this is at 22.5 degrees, and that this is also at 22.5 degrees. It's not the same 22.5, right? It's not the same angle, but they are equivalent. They're just measured from different places. That might be confusing, but hopefully you'll see in a little bit that it's going to make our lives a little easier. All right, now we get to what we need to do. We don't know the value of these 2 forces, but we do know that because they are not on the x-axis and they are not on the y-axis, they have component vectors. Remember, the component vectors are the individual forces that are acting at the same time to produce this force itself. So red's component vectors look something like this. A force that points up and to the right, diagonally up to the right, is pulling both to the right and up at the same time. Force blue, because it's pulling diagonally up to the left, is pulling up and to the left at the same time. Sorry, one other thing that we should know here, right? if it says that this object is motionless, motionless was one of our forms of equilibrium, right? So that means that the net force on this object has to be 0. But, as we've established, in 2 dimensions, that means we have to have equilibrium on the x-axis and equilibrium on the y-axis. Getting back to our problem. If we look at our x-axis, there are only 2 forces on our x-axis, the horizontal component of red and the horizontal component of blue. If we need to have equilibrium on the x-axis, those 2 forces have to cancel. That has to be true, but we don't know what those 2 forces are right now. If we look at the y-axis, there are now 3 forces on the y-axis. Remember, putting our component vectors in is similar to just taking these 2 forces out and replacing them with the equivalent component vectors. If we look at the y-axis now, there are 3 forces on the y-axis. Upwards component red, upwards component blue, downward force of gravity. Because the angles of red and blue given to us were the same, that means that the component vectors are going to be the same. Magnitude. Maybe different directions, like on the x-axis. Maybe not different directions, like on the y-axis. But because the angle that they gave us for each force, red and blue, is exactly the same, 22.5 degrees, that means that the magnitude of these upwards components has to be equal. If that's the case, we have 2 forces upwards balancing out 1 force downward. How much? Each one of those upwards components is going to take half of the load. So if we take 168 and divide it by 2, we get 84. And that means that this one's 84, and that also means that this one's 84. What does that do for us? Well, remember, this component can be made as part of a big triangle, just like this. And we know one of the angles of that triangle, and now we know one of the sides of that triangle. Remember, this all stems from the idea that we got to have equilibrium on the x-axis and equilibrium on the y-axis. There were 3 forces on the y-axis, 2 up, 1 down. The 2 upwards ones have to balance the 1 downward one. Here, in this case, we are actually looking for the hypotenuse of that triangle. That arrow represents force red. Remember, the tension is now doing 2 things, right? Because it's at an angle, it pulls horizontally and vertically. So we're looking for the hypotenuse. The side of the triangle that we know in relation to the angle that we know is the opposite side. If we're looking for the hypotenuse and we know the opposite side, we're going to use sine. Sine theta, opposite over hypotenuse. So that means now we start plugging in things that we know, right? Sine of 22.5 is equal to the opposite, which is 84, over the hypotenuse. Good. Sine of 22.5 equals opposite, which is 84, over the hypotenuse, which we've labeled f sub r. Okay? Sine of 22 is a number. You plug it into your calculator. Sorry, sine of 22.5 is a number, and it turns out to be 0.383. So, if we take this from here and take it down here, 0.383 is equal to 84 newtons over f of r. Now, math. Make sure you do it properly. Your variable is on the bottom of this fraction. There are multiple ways you can do it. I'm going to do it this way. The first thing I'm going to do is I'm going to multiply this side by f of r, and that cancels these f of r's. But if I multiply one side of the equation by f sub r, I got to multiply the other side. Now I'm left with f sub r times 0.383 is equal to 84 newtons. I now divide both sides by 0.383, and I end up with 219.5 19.5 newtons. Now, just to check, right? F of r is the hypotenuse of this triangle, and that means it has to be the longest side. If you do this and you don't do your math right and you get a number lower than 84, which I know some of you are going to do, go back. Mathematically, you can't have a number lower than 84. The hypotenuse always has to be the longest side. So we know that the tension in force R is equal to 219.5 newtons, or going back, sig digs, right? We'd have to round this up, but we'd have to go scientific notation to make sure that all of our numbers gets significant. As far as force B goes, or sorry, force blue, right? Because it's at the same angle, it's going to be exactly the same force. So we don't even have to do any calculations here. We know that force B, or force blue, sorry, is also going to be 220 times 10 to the second newtons as well. Going back to our original agenda, if you look at there, on page 151, problems number 1 and 2, very similar to the gravity problems that we were just working on. And then also from the problem set, the one I gave you on Friday, or the one that you got on Friday, which hopefully will show up here in a second, if my computer decides it's going to cooperate. There it is. All of the problems on the front side of this problem set all deal with adding in that gravity factor and getting equilibrium using gravity. So, taking a look, right, the answers to that problem set are posted online. Make sure you're working on those. I'll be back tomorrow. There's one more type of problem that we deal with equilibrium in 2 dimensions, and now we'll include friction as well into this discussion. We'll go from there. Taking a look at the calendar, don't forget, on Thursday of this week, you will have your first quiz for this unit. It is an open note quiz over the stuff we did Friday, Monday, and Tuesday. We'll do some practice on Wednesday with Static Stations Lab. All right, everybody, I will see you guys tomorrow. Have a good day, and I'll be back.